Hello friends and welcome to SheTech Education YouTube video channel. In today's lecture we are going to study what is the natural frequency of free longitudinal vibration, how to find it. In previous lecture we have studied some basic concepts of vibration. In that we have studied what is vibration, what are different terms used in the vibration, and what are different types of vibration. In today's lecture we will study how to find the natural frequency of a free longitudinal vibration. But before that, we will take a look on what is longitudinal vibration. When the particles of shaft or disc moves parallel to the axis of shaft, or the vibration along the length of that shaft is called as a longitudinal vibration. Now in this first example of shaft and disc, as well as in the second example of spring and mass, if that disc or mass is displaced along the length of that shaft or spring and released, then the vibration of shaft as well as spring will be along its length, and this or parallel to its length. This type of vibration is called as a longitudinal vibration. Now how to find the natural frequency of longitudinal vibration or free longitudinal vibration. There are three methods of finding the natural frequency of longitudinal vibration: equilibrium method, then second is energy method, and third is release method. Equilibrium method, energy method, and release method. We will start with equilibrium method. How to find a natural frequency by using equilibrium method. Now for that, consider a spring of negligible mass in an unstrained position as shown in figure A, having stiffness S. That stiffness you can represent by K as well as S also, K or S. Now that stiffness is nothing but it is the force required to produce the unit displacement in the direction of vibration. It is usually displaced or usually represented by Newton per meter. Now if suppose to that spring I have attached a mass m, then there will be some static deflection of that spring, and that in that equilibrium position, that force applied on that spring due to gravitational pull of that mass is balanced by the force of spring, and such a spring force can be represented by W is equal to K into delta, and that W is nothing but a spring force or the mass or weight of that mass. W is equal to mg, as well as that spring force W is equal to S into delta, whereas delta is static deflection of spring when mass is attached. In that B diagram you can observe, when mass is attached to that spring has been displaced statically, and that deflection is nothing but delta. And if you multiply stiffness into delta, you will get the weight of that mass. Now the mass is now displaced from its equilibrium position by a distance x as shown in figure C. That mass has been displaced by distance x, and it is then released. Therefore it will start vibrating about its mean position, and this is nothing but a free vibration. Previously in definition also we have seen the vibration of that particle or system about its mean position along its length is called as a, or parallel to its length is called as a free longitudinal vibration. Now for this vibration we have to find out the natural frequency. For that purpose, consider that mass is displaced by distance x. At that time we will prepare a free body diagram or free body diagram of that mass as shown in C. There, to that mass I have shown three kind of forces, one in upward direction, two in downward direction. From that one force I will first find out called as a restoring force. Now, while calculating that restoring force, apart from that accelerating force, I will consider all the forces acting on that mass. Now, how many forces? Three forces are acting on that mass. First is upward spring force. What is spring force? Spring force previously we have calculated in B diagram. See there, W is equal to S into delta. In C diagram now, that mass is again displaced by distance x, therefore that W or spring force will be S into delta plus x. See in that C diagram. Then one more force in downward direction will be there, that is W. W is equal to mg, its self weight, along with the accelerating force. Therefore three forces will be acting at the equilibrium diagram or free body diagram. Now in that free body diagram, apart from that accelerating force, mass into acceleration, m into d2x by dt square, apart from that force, two forces are there, and that we will consider by taking upward force as a negative and downward force as a positive. Therefore, what will be restoring force? W minus S into delta plus x. Simplified, W minus S into delta minus S into x, where W is equal to S into delta. Therefore, I will get as equation 1, restoring force is equal to minus S into x. In some reference books, you may observe instead of S, stiffness may be considered as a K also. Here I have considered it as a S for this derivation. Therefore, restoring force is equal to minus S into x. Call it as equation number 1. Now, this restoring force is opposed by one accelerating force. Accelerating force in downward direction, m into or mass into acceleration, m into d2x by dt square. If x is displacement, then d2x by dt square, second order derivation of that displacement, will be acceleration. Therefore, mass into acceleration will be accelerating force. Call it as equation number 2. Now, equating these two equations 1 and 2, I will get minus s into x is equal to m into d2x by dt square. Simplify this equation and make equation such that t2x by dt square plus s by m into x. Call it as equation number 3. Now we know that the fundamental equation of SHM, that is simple harmonic motion, is represented by d2x by dt square plus omega square into x is equal to 0. Now whatever third equation we have got by equating restoring force and accelerating force, we have got d2x by dt square plus s by m into x. Compare these two equations, standard equation of SHM and third equation whatever we have got, we will get omega is equal to square root s by m, or omega is equal to square root k by m. Instead of s, if I put k, then it will be omega is equal to square root k by m, or omega is equal to square root s by m. This will be omega. And what is omega? Omega is circular natural frequency, remember, or circular frequency. Omega is equal to square root s by m. Therefore, time period, we are knowing that time period is 2 pi upon omega. 2 pi upon omega. This is the time period of SHM. Then omega we have got is square root k by m or s by m. Put the value of that. Time period you have got 2 pi into square root m by s. Frequency, natural frequency is, you are knowing that it is a reciprocal of time period. Natural frequency is reciprocal of time period. Remember that time period you have just now found, it is 2 pi into square root m by s. Frequency is equal to now reciprocal of that time period, that is 1 upon twice pi square root s by m. Remember this formula. This is the formula for natural frequency of longitudinal vibration. Fn is equal to 1 upon twice pi square root S by m, or Fn is equal to 1 upon twice pi square root K by m. Remember this. Now we will simplify furthermore same formula little bit. In some problems it is required like this simplification, so we will simplify it. Since now in this diagram observe your W is equal to delta into S, whereas W is equal to mg as well. Therefore spring force and this weight are equal in B diagram. Mg is equal to S into delta. Therefore I can write in that square root value, instead of square root value S by m, I can write G by delta, where G is 9.81. Put the value of G as 9.81. You will get the frequency value as 0.4985 divided by square root delta. This will also be a formula for natural frequency of longitudinal vibration. Now note that the value of this static deflection delta can be found from the given conditions in the problem, and for longitudinal vibration it may be obtained by one relation, that is stress by strain is equal to E. E is Young's modulus. Stress by strain is equal to E, or stress you can find out in this problem as W by A into L by delta is equal to E. Delta is equal to WL by AE, or E into A. This will be delta, static deflection. In some problems you have to use this formula, delta is equal to WL by EA, to find out delta and put the value of delta in the frequency formula and find out natural frequency Fn by formula 0.4985 divided by square root delta. This is the frequency of longitudinal vibration by equilibrium method. What we have done in equilibrium method, we have drawn a free body diagram. In that we have found the restoring force and equated with accelerating force. By equating we have got one equation and compared it with standard equation of SHM, and we have got omega is equal to square root S by m. From that omega we have found time period, because we know time period of SHM is equal to twice pi upon omega. And next we have found frequency, because frequency is reciprocal of time period, and formula ultimately we have got is Fn is equal to 1 upon twice pi square root K by m, or Fn is equal to 1 upon twice pi square root S by m. Now same thing or same formula we have to derive by another method, that is energy method. Another method, that is energy method. Now in energy method what we have to do, we have to consider, or we know that the kinetic energy is due to the motion of body and potential energy is with respect to certain position, which is equal to amount of work required to move the body from datum position or mean position. In case of vibration, the datum position is mean or equilibrium position, at which potential energy of the body is zero. Now in free vibration, by equilibrium method, if you want to find out natural frequency, remember this condition: no energy is transferred to system or from the system. No energy is transferred to the system and from the system. Therefore the summation of kinetic energy and potential energy must be constant quantity, which is same at all the time. In energy method it is considered that the summation of kinetic energy and potential energy is constant. Therefore if we take the derivation of this kinetic energy and potential energy, then we will get the kinetic energy plus potential energy derivation with respect to time t is equal to 0, because derivation of constant value is 0. Therefore we have got this equation: d by dt of kinetic energy plus potential energy is equal to 0. Now we will put the values of kinetic energy and potential energy in that equation. Kinetic energy is equal to 1/2 Consider in that diagram, if I attach mass and displaced by distance x and released, it will vibrate with a free longitudinal vibration. At that time, the kinetic energy will be 1 half m into v square, where velocity will be dx by dt. Because displacement is x, velocity will be dx by dt. Kinetic energy is 1 half m into dx by dt square. Potential energy will be, remember this, potential energy in this case is mean force into displacement. Mean force into displacement. What is mean force? Initially force is 0. Secondly, there is a restoring force, that is s into x. S into x, spring force, divided by 2. 0 plus s into x divided by 2 into displacement is x. Therefore, ultimately potential energy we will get as a 1 half s into x square. 1 half s into x square. Therefore, put this value of kinetic energy and potential energy in the equation, above equation of d by dt of kinetic energy plus potential energy equal to 0. By putting this and simplifying, finding the derivation, we will get an equation d2x by dt square plus s by m into x is equal to 0. Again, we have got one equation, differential equation, second order differential equation. Now compare this equation of motion with the standard equation of SHM, simple harmonic motion. What is standard equation of SHM? d2x by dt square plus omega square into x is equal to 0. Therefore, by comparing this equation with d2x by dt square plus s by m into x, we will get omega is equal to square root s by m. Same omega we have got for equilibrium method also. See, omega is equal to square root s by m. Further, the procedure will be same as that of equilibrium method. After finding omega, find out time period. Time period is equal to twice pi upon omega. Frequency is equal to 1 upon time period. Therefore, frequency for this case also we have got, by energy method also we have got, Fn is equal to 1 upon twice pi square root k by m or square root s by m. Now, by Rayleigh's method also we have to find the natural frequency of longitudinal vibration. Again, ultimately we will get same formula, that is 1 upon twice pi square root s by m, but we will derive. Now in this Rayleigh's method, it is considered that the maximum kinetic energy at mean position is equal to maximum potential energy at extreme position. Maximum kinetic energy at mean position is equal to maximum potential energy at extreme position. Remember that during oscillation or vibration, the potential energy will be maximum at extreme position and kinetic energy will be maximum at mean position. And it is considered by Rayleigh that these energies at mean position and at extreme position are equal. Therefore, we will find out this kinetic energy and potential energy and equate them. Since you are knowing that the vibration, this type of vibration can be considered as a simple harmonic motion, therefore x can be written as capital X into sine omega t, where small x is the displacement of body from the mean position after time t, and capital X is the maximum displacement from the mean position at extreme position. Small x is displacement and capital X is maximum displacement. Therefore, differentiating this equation 1, we will get dx by dt is equal to omega into capital X cos omega t. Since at mean position t is equal to 0, therefore this cos omega t will be 1, Then we have got dx by dt is equal to omega into x. This is nothing but a velocity. Dx by dt is equal to omega into x. Now maximum kinetic energy at mean position. We find the maximum kinetic energy at mean position equal to 1 half mv square. V just now you have found as a omega into x. Put it. Then we have got equation number 2 as 1 half m omega square into x square. Maximum potential energy at extreme position, again you have to find out by formula mean force into displacement. Mean force will be 0 plus s into x divided by 2 into capital X. We will get 1 half s into capital X square. Call it as equation number 3. Equating equation 1 and 2, because in Rayleigh's method it is considered that maximum kinetic energy at mean position equal to maximum potential energy at extreme position. Equate these two, you will get omega square is equal to s by m, nothing but omega is equal to square root s by m. Further procedure is same. Once you find omega as a square root s by m, next is time period is equal to 2 pi upon omega, and frequency is equal to reciprocal of time period. You will get frequency formula as 1 upon twice pi square root s by m. Now note that in all above expressions, omega is nothing but a natural circular frequency and generally denoted by omega n. Omega n. Frequency is equal to omega n divided by twice pi. Nothing but 1 upon twice pi square root s by m. Isn't it? These are the three derivations by which we can find out the natural frequency of longitudinal vibration. First is equilibrium method, second energy method, and third as Rayleigh's method. By all these three methods you have find the frequency Fn is equal to 1 upon twice pi square root k by m, or 1 upon twice pi square root s by m. Now we will, if you are going to find out the natural frequency of spring and mass system which are vibrating with longitudinal vibration, then in many times in application, in actual application, these springs are not a single spring. There are multiple springs attached serially as well as parallel in the form of n number of springs. So we need to find out the equivalent spring stiffness of all these springs. Therefore there are two conditions, that is springs in series combination and springs in parallel combination. We will find out the equivalent spring stiffness for both the conditions, and then we can find out the natural frequency of longitudinal vibration of the system. We will solve some problems as well. Now first consider that a first condition, that springs in series combination. Consider the diagram. In that one mass is attached to two springs which are in series, that is K1 and K2 are connected one after another. Therefore these two springs are in series, whereas K1 and K2 is the stiffness, spring stiffness of these two springs. Now if suppose springs are in series, then the force that each spring will experience will be same. Remember this thing. If you are attaching one mass to these two springs in series and displacing this mass and tend to vibrate this mass longitudinally, then these springs K1 and K2 will experience the same force, and total displacement of mass from equilibrium will be, total displacement of this mass will be x1 plus x2, that is displacement due to displacement of spring 1 plus displacement of spring 2 will be equal to total displacement, that is x. This is regarding springs in series. For springs in parallel, remember the force is not same here. Force is distributed, but their displacement will be same. K1 and K2 in this diagram are connected in parallel to the mass. Their one end is attached to fixed and one end is attached to mass. Therefore, the force will be distributed equally, but their displacement will be different. Remember this thing. Sorry, their displacement will be same, but force will be distributed in this parallel condition. Now, consider a series condition in which x is equal to x1 plus x2. We will derive something to find out the spring stiffness, equivalent spring stiffness for a springs in series. Now, x is equal to, if suppose you are going to find the spring stiffness, then you are knowing that force is equal to k into x, where x is equal to now F divided by k. Therefore, for spring 1, the x1 displacement will be F1 divided by k1. For spring 2, x2 is equal to F2 divided by k2. Similarly, from that first equation, x is equal to x1 plus x2, we can write x1 plus x2 is equal to Fb by k equilibrium. Fb is total force acting on that, and k equilibrium is the equivalent spring stiffness due to k1 and k2 stiffnesses. Therefore, substituting the value of x1 and x2 into latter equation, we will get f1 by k1 plus f2 by k2 is equal to fb by k equivalent. Therefore, you are knowing that f1 and f2 is equal to fb, that is total force. You are knowing that if springs are in series, force will be equal in all. F1 is equal to F2 is equal to Fb. Therefore, it will cancel out, and remaining equation is 1 upon k equilibrium. Sorry, 1 upon k equivalent is equal to 1 upon k1 plus 1 upon k2. If suppose such n number of springs are there, that is k1, k2, k3, k4 and kn up to kn, then the equation for the equivalent spring stiffness will be 1 upon k equivalent is equal to 1 upon k1 plus 1 upon k2 plus 1 upon k3 plus 1 upon k4 up to plus 1 upon kn will be there. This is the method to find out the equivalent spring stiffness. Remember this last equations in square bracket. Next, if suppose springs are in parallel, then both the springs are touching to the block in this case, and whatever distance of spring 1 is compressed, same will be for spring 2. Therefore, these spring will be in the parallel combination. Remember, if these two springs are compressing and elongating with the same magnitude, that is deflection is same, then the springs are in parallel. If force distributed is same, then the springs are in series combination. Here the deflection is same. Therefore, force will be divided in these two springs. Fb is equal to F1 plus F2 I can write. You know the equation, F is equal to k into x. Therefore, F1 I can write as a k1 into x, and F2 I can write as a k2 into x. This x will be same, displacement of these both spring will be same. Therefore, Fb is equal to minus k1, sorry, neglect that minus sign because this force is opposite, that's why I have considered there a minus sign in previous also. Sorry, not in previous, in this equation I have considered as a minus, neglect that minus sign. Fb is equal to k1 plus k2 into x. Therefore, for equilibrium, sorry, equivalent, k equivalent is equal to k1 plus k2. Remember, this is square bracket equation. For springs in parallel, if suppose n number of springs in parallel such as k1, k2, k3 and up to kn stiffnesses, then the final equation for springs equivalent spring stiffness I can write as k equivalent is equal to k1 plus k2 plus k3 up to kn, like that. For remembering that, I have prepared this table. Remember this table directly to solve the problems. Quantity, springs in series and springs in parallel. Equivalent spring stiffness or equivalent spring constant for springs in series. It can be found by formula 1 upon k equivalent is equal to 1 upon k1 plus 1 upon k2. For springs in parallel, it will be k equivalent is equal to k1 plus k2. Now deflection or elongation for springs in series is not equal, but in springs in parallel it is equal. See in that diagram also, for k1 and k2 springs deflection will be same for parallel condition. Now force will be same for springs in series, but it is not same for springs in parallel. Remember through this table. Now we will solve some problems based on this springs in series and parallel, how to find out equivalent spring stiffness and the natural frequency of the system. Now see the first problem. A 160-gram object attached at one end of a spring and spring stiffnesses are K1 is equal to 500 Newton per meter, K2 and K3 are equal and is equal to 800 Newton per meter. These are stiffnesses. What is the natural frequency of spring and mass system having three springs connected in series and parallel as shown in the below figure? Now in this figure you are observing that K2 and K3 are springs which are in parallel combination, whereas the equivalent spring stiffness of K2 and K3 is in series with K1, and after finding that you will get the equivalent spring stiffness of the system. First you have to find out the equivalent spring stiffness or equivalent spring constant of the system, then you can find out the natural frequency of the system. To find out equivalent spring stiffness, consider the spring 2 and 3 which are connected in parallel. So what is the formula to find out the equivalent spring stiffness between parallel combination? It is K23 is equal to K2 plus K3. Find out that. Consider now this spring 1 and equivalent spring stiffness K23 are in series combination. Therefore apply the formula for the series combination as 1 upon k is equal to 1 upon k1 plus 1 upon k23. You will get the spring stiffness, equivalent spring stiffness as a k. This will be spring stiffness equivalent for all these springs. Therefore put this spring stiffness in the formula of natural frequency of longitudinal vibration. K Fn is equal to 1 upon twice phi square root k by m. So k put as a k equivalent and m as mass in kg. Therefore you will get the frequency Fn is equal to 7.76 Hertz. This is the first problem. Now in second problem, two springs are there. Initially they are in parallel combination, and this parallel combination is again in series with another spring. So here also we have to find out natural frequency. We know the formula for natural frequency is 1 upon twice pi square root k by m, but for that we have to find out the equivalent spring stiffness k. That first we will find out. First two springs are in parallel. For parallel, equivalent spring stiffness can be found as summation of the two stiffnesses, that is summation of k, because k is same, k plus k, you will get k1. Then these parallel springs are in series with 2k. Therefore for series combination use the equivalent spring constant formula. 1 upon k is equal to 1 upon twice k plus 1 upon k1. Applying that we will get the stiffness k as 5000 Newton per meter. Then put in the formula of natural frequency, you will get a frequency Fn is equal to 3.56 Hertz. These are simple problems. Next, one more problem is there. A cantilever shaft of 50 mm in diameter and 30 long, has a disk of mass 100 kg at its free end. The Young's modulus for the shaft material is 200 giganewton per meter square. You have to convert this Young's modulus into Newton per meter square by multiplying 10 raised to 9 to convert giga into Newton. 10 raised to 9. Determine the frequency of longitudinal and transverse vibration of shaft. Transverse we have not studied yet, therefore we will find out the natural frequency of longitudinal vibration only. Now the formula for natural frequency of longitudinal vibration is 1 upon twice pi square root k by m, or one simplified formula previously we have studied in this video only. Fn is equal to 0.4985 divided by square root delta. In that, delta is static deflection. Therefore in this formula unknown is only delta. Therefore we have to find out delta. How to find delta? Delta for that cantilever beam is delta is equal to WL by AE, A into E. Therefore W is weight of that mass attached. Mass is given in this problem as 100 kg. L is the length of that shaft. It is given 300 convert into meter. A is the area of cross section. Now area of cross section of the shaft can be found promised diameter as pi by 4 into d square. Then E is the Young's modulus converted into Newton per meter square and use there. Therefore delta I have got WL by AE. I have found delta first. Put the value of delta directly in the formula of natural frequency. Fn is equal to 0.4985 divided by square root delta is equal to, I have got a natural frequency 575 Hertz. This is also the way to find out the natural frequency of this kind of problems. Now next I have given one problem for solving at a home for you. Do it yourself. What is the equivalent spring stiffness of the system given in this diagram? In this diagram, K is the stiffness, M is the mass of that mass in the system. Use the previous knowledge of springs in series and parallel and find out equivalent spring stiffness. Previously we have solved many problems to find out the stiffness first and then find out the natural frequency, but here I have asked only find out this equivalent spring stiffness and comment in the comment box right answer. So subscribe my channel. Thanks for watching. In next videos we will study the another types of vibration, that is transverse vibration and torsional vibration. Thanks for watching.